It is my great pleasure to introduce the first keynote speaker of tonight. It is Mike Cuffaro from Munich. We all know Mike. He is, among many other things, the co-author of the book Understanding Quantum Warfare's Quantum Mechanics on an Informational Approach, Structure and Interpretation. So if you have not read the book yet, you should do so immediately after the conference. And today, Mike will talk about quantum mechanics on an informational or neo-Bohrian approach. The floor is yours.
Thanks for the kind introduction, and thank you for inviting me to this workshop. And I hope I can continue the great series of talks that have happened so far. So I'll begin by specifying which informational interpretation I'm going to be talking about today. So because there are a number of them, of course, and we saw some versions of informational approaches yesterday. So what I'm going to be discussing in particular is the view that we, the authors of the book Understanding Quantum Raffles that Philipp mentioned, like to call boobism, which rhymes with cubism, of course, but it's not cubism. And I'll specify, I'm not going to talk about the ways in which they differ so much, but I'm just going to lay out the view that we want to defend. And so the view is called boobism. It's named after Jeffrey Boob, but properly speaking, you might want to call it the Boob-Potofsky / Dimopoulos view. And so it begins with the ideas of Vudimir-Potofsky, beginning with this book in the 1980s, Quantum Probability, Quantum Logic. It's been defended especially, and hence the name boobism, by Jeffrey Boob, especially, most recently in these two books, Banana World and this popular book, which is a graphic novel that he wrote with his daughter Tanya Boob. And although Bill Dimopoulos probably, I don't think he would have wanted to use the label informational to characterize his view. I also don't think, although he and Jeff were very good friends, I don't think he would want to use the term boobism to describe his view either. But I think the ideas there are close enough to Jeff's and Itamar's that I think it makes sense to describe them and the view that we defend in our book as part of the same overall family of views. And so speaking of the book that we defend, this is the book that Philipp just mentioned, Understanding Quantum Raffles. It also has a foreword by Jeff. And before I begin, I just want to mention that our view is, we take it that we have our own distinctive view of quantum mechanics, but we do think that our view is somewhat similar to a number of others. So for instance, we think it's somewhat similar to Czeslaw Bruckner's and Anton Zeilinger's view, although the terminology is different in some instances. Other people who we agree with more than we disagree with are pragmatist interpretation of Richard Healy, cubism, defended by Chris and Rudiger and others, and more distantly related views, I would say, are the relational interpretation, Carlo Rovelli's original version from the 90s, as well as the one that he defends more recently with Emily Adlam. And before I begin, I just also want to clarify what I mean by neo and neo-Bohrian. So what this means essentially is, boobism can be thought of as a neo-Bohrian position in the sense of amounting to an interpretation of Bohr, or at least what we take to be essential about Bohr's view, and an elaboration of how to make sense of what we have learned about the world since Bell in neo-Bohrian terms. That said, the intention here isn't to make a contribution to the historical scholarship on Bohr. So if you agree that the view captures what's essential to Bohr's view, then you can feel free to call it a Bohrian view. Otherwise, feel free to call it neo-Bohrian. Ultimately, we don't care about labels like that. It's the content of the view that we're concerned with. But speaking of Bohr, I'll begin with a quote from Niels Bohr to Paul Dirac. And so in a letter that he wrote to Paul Dirac from March 1928, Bohr writes, "I quite appreciate your remarks that in dealing with observations, we always witness through the permanent effects a choice of nature between the different possibilities. However, it appears to me that the permanency of the results of measurements is inherent in the very idea of observation. Whether we have to do with marks on a photographic plate or with direct sensations, the possibility of some kind of remembrance is, of course, the necessary condition for making any use of observational results. It appears to me that the permanency of such results is the very essence of the ordinary causal space-time description. This seems to me so clear that I have not made a special point of it in my article." By that he means a complementarity paper. And I would insert a rather here. So rather, what has been in my mind above all was the endeavor to represent the statistical quantum theoretical description as a natural generalization of the ordinary causal description, and to analyze the reasons why such phrases like a choice of nature present themselves in the description of the actual situation. In this respect, it appears to me that the emphasis on the subjective character of the idea of observation is essential. Indeed, I believe that the contrast between this idea and the classical idea of isolated objects is decisive for the limitation which characterizes the use of all classical concepts of quantum theory. Especially in relation to the transformation theory, with the transformation theory, the situation may, I think, be described by saying that any such concepts can be used unaltered if only due regard is taken to the unavoidable feature of complementarity. And so the rest of the talk will be, in some sense, just unpacking this long quote. So let's start with this phrase that I highlighted, the necessary condition for making use of observational results. So what are observational results? So what we mean by this is not sense data necessarily, or not direct sensation. An example of observational results, we would argue, is something like Newton's phenomena, the phenomena that Newton uses to argue to the conclusion to the conclusion of universal gravity. And so I'll read the first one. So the first phenomenon that he uses in that argument is the circumjovial planets, by radii drawn to the center of Jupiter, describe areas proportional to the times, and their periodic times, the fixed stars being at rest, are as the 3/2 powers of the distances from that center. I won't read the rest because they're all similar. The upshot of this is the idea that physical phenomena can be mathematized. So what we're discussing here are not merely direct. This is not merely direct sensation. It's similar to the kind of claim that Bogan and Woodward, for instance, in philosophy of science, have made about phenomena as distinct from direct sense data. In the context of statistical data, George Boole in the 19th century derived what he called a number of conditions of possible experience, which he argued were such that when satisfied, they indicate that the data may have, and when not satisfied, they indicate that the data cannot have resulted from an actual observation. So the idea here is that if you consider a given set of rational numbers, P1 through Pn, that represent the relative frequencies of n logically connected events E1 through En. We ask the question, what are the necessary and sufficient conditions under which the Pi can be realized as probabilities corresponding to the logically connected Ei in some probability space? And there's a general algorithm for determining these conditions, which was laid out by Itamar Potofsky in this paper that I referred to here, the 1994 paper. And so the algorithm goes like this. Given some set of logically connected events, E1 through En, write down a corresponding propositional truth table where you put the E1, the events up there. Then you associate each row of this truth table with a vector of extremal probabilities, P1 through Pn. Then take the convex hull of these vectors to yield a polytope. And then determine the linear inequalities that are associated with its facets. And these are the so-called conditions of possible experience. A special case of these, as Potofsky showed, is the Bell inequalities. So the Bell's inequality corresponds to one of these facets in a particular setup that's considered in that context. Now, in the book, in our book, we showed, or rather Michael Janeth showed, although the result isn't original to us, this is a result from the 19th century, essentially. We derived a general nonlinear constraint on the correlations between three balanced random variables in a particular setup. It's the Merman setup, Merman's derivation of the Bell inequalities, or of his version of the Bell inequalities. So we derived this constraint where the row of xy corresponds to the Pearson correlation coefficient for two balanced random variables x and y, where these are the sigmas are the standard deviations. Now, we show that to derive this, there's an important step in the derivation where we rely on the fact that we can take a linear combination of the three variables, like so. And the next thing we do is we model this relation in a local hidden variables theory. And modeling this in a local hidden variables theory requires a joint probability distribution over the values of x, y, and z. The consequence is that in a local hidden variables theory cannot fully saturate the elliptope. So you can think of the elliptope as the correlational space corresponding to the particular setup that we're considering. And when you try to recover that in a local hidden variables theory with 2 values per ticket, and the tickets are our toy variable model, then you don't saturate the elliptope. You just get this tetrahedron. You can only saturate the elliptope as you increase the number of outcomes per variable. So for 3 values per ticket, you get that, which is a little bit closer to the elliptope. For 4 and 5 values, you get figures that are closer and closer to the elliptope, but it becomes computationally much harder to calculate this as you increase the number of values. And then as you go to infinity, you get closer and closer to the elliptope. Now, if you model this relation in quantum mechanics, you find that you get saturation of the elliptope for all values of spin. So a spin corresponds to a raffle ticket, right? So spin a half, you have a 2 outcome ticket, and so on. And so in the quantum mechanical case, you get saturation of the elliptope for all values of spin. You already have saturation even in the spin a half case. And the reason is that in quantum mechanics, at least in this setup, the reason stems from the fact that in quantum mechanics, we can assign a value to a sum without assigning values to the summands. Can I close that? Is that okay?
Yes, sure.
Yeah. Oh, what happened? Oh, what happened? Maybe I shouldn't have closed that. Okay. Okay, there we go. Okay. So assigning a value to a sum without assigning values to the summand is something that isn't possible in classical theory in the sense that the kinematics of quantum mechanics, whereby kinematics I mean the kinematical constraints that are imposed by the theoretical framework of quantum mechanics on our physical description of a system independently of the specifics of its dynamics. So the kinematics of quantum mechanics are less restrictive. For instance, you can define an operator S hat by taking a linear combination of 3 operators S hat, A, B, and C. So in essence, we make the claim that quantum mechanics is all about information or all about probabilities. That's what we mean. We mean that the kinematical constraints are less restrictive in that sense. So it's not an ontological claim. Rather, this is a slogan. It's just a claim about where the conceptual novelty of quantum mechanics lies, in the way that the kinematical constraints of quantum mechanics constrain our probability assignments. The slogan also conveys the idea that quantum mechanics is a framework that can in principle be applied to any type of physical system. For example, computational systems, the fictitious quantum bananas of Jeff's Banana World book, the coins of Totally Random, and so on. So understanding why quantum mechanics, but not classical mechanics, allows us to saturate the elliptope for all values of spin. That's just one example of a problem that can be solved by appealing exclusively to quantum mechanics kinematical constraints. And so I won't go through these in detail because I'm not the historian in the group. That's my co-author, Michelle Janssen. But there are further examples from the history of quantum mechanics of physical problems that seem to call for dynamical solutions, but that were solved simply by appealing to the quantum theory's kinematics. And for example, the problem of accounting for the particle term in Einstein's 1909 formula for energy fluctuations in blackbody radiation. The problem of accounting for the formula for the electric susceptibility of diatomic gases. The problem of accounting for why electron orbits seem to depend on which coordinates you choose to impose on the quantization condition. And this is all laid out in section 6.4 of the book. So now I'll move on to the second part of the long Bohr quote that I showed. So the idea that quantum mechanics can be thought of as a natural generalization of the ordinary causal description. So to get into this, let's begin by comparing classical mechanics and quantum mechanics. So in classical mechanics, specifying a system's state yields an answer to every yes or no question that can be asked about a particular observable quantity. For example, is the value of the observable A within the range delta? So the classical state is a truth maker. So not in the heavy metaphysical sense of truth maker, because it's become a technical term in metaphysics, but I just mean in a logical sense, in the sense that the classical state determines the answer to every yes or no question about the quantity, irrespective of how we happen to be interacting with the system. Further, that's simultaneously true of all observables. So the state determines the answers to all questions concerning all observables in advance. In quantum mechanics, by contrast, the states fail to be truth makers in two different senses. The first corresponds to what people have called the big measurement problem. The term originates with Potofsky. And this is the problem that specifying psi yields in general only the probability that the answer to a given experimental question will take on a given value. Now, just want to note that that's not as much of a departure from classicality as one might think, because conditional on the selection of an observable, the observed statistics are describable by a classical probability distribution. I'll get back to that a little bit more later. The second sense in which quantum mechanical states fail to be truth makers corresponds to what some people have called the small measurement problem. And this is the idea that the classical probability distributions that are associated with individual observables cannot be embedded into a global classical probability distribution over all observables. So in quantum mechanics, you can only say that conditional upon inquiring about the observable quantity A, there's a particular probability distribution that one can use to characterize the possible answers to that question. And yet, quantum mechanics' unitary description of a measurement interaction doesn't by itself prefer any one of these. And this is analogous to what Everettian, well, it's the same thing, essentially, of what Everettians call the preferred basis problem. So slightly more formally, I'll just repeat what I said. So in classical mechanics, an observable A, we associate with an observable A a function f of A acting on the phase space of the system. Similarly, in quantum mechanics, we associate an observable A with an operator A hat acting on the Hilbert space of the system. So in that sense, that's still very similar. In classical mechanics, with f of A, we can associate a Boolean algebra, curly A, of yes or no questions concerning A. And similarly, in quantum mechanics, we can do something similar. Now, here is where we begin to differ. Points in phase space in the classical case are truth makers in the sense that I described earlier, in the sense that fixing omega, the state of the system, fixes the values for every observable quantity. And the Boolean algebras corresponding to each observable are embeddable into a globally Boolean algebra. In the quantum mechanical case, vectors are not truth makers. Fixing A only fixes the conditional probability that I get a particular value of VA given my inquiring about the observable A and so on. And the Boolean algebras corresponding to the observables are not embeddable into a global Boolean algebra. And so for the rest of the talk, I want to say a bit about how we should construe the wider significance of this. And to start, I want to contrast our view by looking, to begin with, at the motivation for a more ontological understanding of quantum mechanics. And so the way I would characterize this is that we can think of, in philosophy of physics, this traditional metaphysical picture, so-called. It's more or less taken for granted in a lot of the literature. And so on this traditional metaphysical picture, that as I want to call it, dynamical variables like position, momentum, the direction of a particle's spin, and so on, these are understood as a manifestation of an underlying reality whose properties are such as to give rise to the values of the observable quantities that are revealed in our experiments with physical systems. So this, I take it, is what John Bell meant when he wrote that a physical theory should be such that observables are made in some literal sense, in some thick ontological sense, out of beables. But since in quantum mechanics, the values of observable dynamical quantities can't in general be consistently interpreted, at least not in a natural way, because of the big and small measurement problems, as representing the antecedently given properties of a physical system. In other words, since there's no Boolean algebra of properties that we can assign to all of the system's observables, there's two options. And the first option is to posit further quantities over and above what are described by quantum mechanics as the hidden variables program. And the second option is to argue that in principle, all of the approximately classical physical possibilities that are described by a given state vector are realized in some sense, and that's the Everettian option. Now, on the informational interpretation, so we're not opposed to the traditional metaphysical picture per se, in the sense that that picture would be apt if classical mechanics were fundamental. But we're also open to the possibility that it's not apt. Because how we carve nature at the joints, on our view, is something that should be motivated by physical theory rather than posited a priori. So it's important to emphasize that our view is instrumentalist in the sense that we begin from phenomena. But instrumentalism needn't apply anti-realism. Because it depends on what you mean by realism. If what you mean by realism is that, then you're begging the question. But in any case, so it depends on what you mean by anti-realism. And specifically for us, the important question is not whether, but how to assign physical properties to what we take to be the external world. In other words, what's primary for us isn't the traditional metaphysical picture. What we take to be primary, rather, is the empiricist methodology through which we reason from the values revealed in experiments, carried out under precisely specified experimental conditions, to a picture of the world that is anchored in the contextual models one gives of phenomena under the dynamical assumptions characterizing each. So for an informational interpreter, in other words, probabilities are, strictly speaking, always defined conditionally, always defined relative to a given experimental context. And the picture that our theories built up of the world is, in that sense, essentially a contextual picture. But of course, that can admit of special cases, of which classical theory is one, in the sense that in classical theory, although this is still true, the experimental context can, in a very natural way, be abstracted away from, so that we can think of probability assignments as absolute. And so the sense in which we can think of classical theory as a special case is exactly the sense that I showed you earlier, right? So this is a special case of this more general correlational space. So what's exhibited by the quantum state, in our view, isn't per se a collection of antecedently given properties possessed by a system, but rather the structure of and interdependencies among the possible ways that one can effectively characterize a system in the context of a physical interaction. Indeed, that's no less true of a classical state description, which is another way of saying what I said in the last slide. And so for that, you may want to have a look at Eric Curiel's characterization of an abstract classical system, which is essentially this as well. But because the probability distributions over the values of every classical observable are determined independently of whether a physical interaction through which one can assess those values is actually made, in the sense that determined logically, in the sense that we know what they are, there's an invitation to think of them as originating in the properties of an underlying physical system that exists in a particular way, irrespective of anything external. There's an invitation to do that. But the more complex structure of observables related by quantum mechanics doesn't similarly invite the inference from the values of observable quantities to the properties of an underlying system in that sense. That said, in a given measurement context, which we can by assumption describe effectively in Boolean terms, one can give a dynamical model of the system for that context, also in such terms. Such a model doesn't suffer from the small measurement problem in a given context because the observables associated with that context commute. It does suffer from the so-called big measurement problem, the idea that experimental outcomes are stochastic. However, in any given measurement context, it will always be possible to effectively interpret, this is just the idea that it comes from no signaling, essentially. It will always be possible to effectively interpret the indeterminacy of individual measurement results in a given experimental run as stemming from our inability to specify some relevant physical parameter in whatever dynamical model that we use to conceptualize the phenomena in that context. Moreover, the probability distributions that one can assign in the various measurement contexts associated with the system on the basis of a given state psi are quantitatively related to one another in a consistent way that is constrained by the kinematical framework of quantum mechanics. So someone may object, but can nothing really be said on this informational view about what the world is like independently of observation? And well, on the contrary, on the one hand, we have non-dynamical quantities like mass, spin, charge, and so on. Assignments of values to these quantities are valid regardless of the experimental context. As for dynamical quantities, the ones that we've been talking about during this talk, well, even in that case, the world is such that all of the effectively classical, and by classical I just mean Boolean, probabilistic pictures that one can draw of it under the precisely specified experimental conditions corresponding to each of them are precisely relatable to one another in the way described by quantum mechanics. That's not a trivial thing. Now, you might ask, does B depend in some sense, physically or metaphysically, on the existence of conscious observers? Well, we would say no. Rather, what's happening here on this view is that a schematic representation of what relevantly constitutes an observer, like essentially a classical conditional probability distribution, or in other words, a Boolean frame, is being used as a formal tool with which to describe how the various dynamical possibilities, which you might think of as propensities, so I don't necessarily want to commit us to a Popperian interpretation of probability, but it's a formal tool to describe how these various dynamical possibilities that are implicit in the physical world are necessarily related to one another. So I won't read these quotes, but Howard Stein and Eric Curiel, for instance, have argued that in the context of classical theory, for all practical purposes, one needs to employ a schematic representation of an observer if theoretical claims are to have epistemic content at all, right? And so on a Bubist understanding of quantum theory, one can think of quantum mechanics as elevating this insight to the level of postulate. So for a Bubist, physics is in the business of describing the true empirical relations that obtain in the world. Of course, that doesn't amount to the description of a substance existing in itself in the traditional metaphysical sense, because schematic or not, there's a necessary relation to a subject, right? But on the empiricist perspective that's embraced by the informational interpreter, we were never committed to that traditional metaphysical picture in the first place. So it's not an objective that we haven't solved the measurement problem, because we don't take it to be a problem. So our view in a nutshell is pretty much this. So quantum mechanics is about probabilities. So these are understood objectively in the sense that they're, to use von Neumann's phrase, given from the start. So as the conditional probabilities are non-contextual. They're assigned by the quantum state, and they're associated with a given concrete measurement context, so which we can think of analogously to propensities. Quantum mechanics describes the relations between these in an in general non-Boolean way, which amounts to saying that the various probability distributions that we can use to effectively characterize a phenomena associated with commuting sets of observables can't be embedded into a global probability distribution over the simultaneous values of all observables. Despite that, quantum mechanics provides, in any given measurement context, a recipe through which one can acquire information concerning a quantum system through interactions with objects whose relevant parameters can effectively be described using classical, in other words, Boolean means as being either on or off with a certain probability determined by the dynamical properties of the system according to the dynamical model that one constructs of it in that context. In other words, and this is the link to the empiricist methodology point that I made earlier, quantum mechanics allows us to do physics in much the same way as we always have. But it does not follow from any of this that nature itself must be such as to allow, in a natural way at any rate, for a globally Boolean description of all aspects of all dynamical phenomena that physics is concerned to describe. And that's it.
Okay, so Chris.
I wouldn't mind a question. Or maybe it's not a question. Could you go back to one of the slides? You don't have numbers on your slides.
I don't have numbers.
But look for a footnote to Eric Curiel.
There's a couple of them.
Not that one. That one. That one right there.
Mm-hmm.
For whatever it's worth, you know, there's maybe a little more than just Boobism and Cubism. They rhyme. So maybe there's another sense in which they rhyme. And I liked your on the contrary A and B, because I think at least there's an analogy or potentially a mapping between Boobism and Cubism right there. So A is that, so what do you say? But nothing can really be said on the informational view about what the world is like independently of observation. A, non-dynamical quantities, like spin, mass, charge. In the early days of Cubism, Carl Caves would, or proto-Cubism before we all made a split, Carl Caves would emphasize that that we never had a problem with the timeless properties of systems. He would call them like mass, spin, charge. And he thought these are elements of reality. And then B, dynamical quantities. The world is such that all the effectively classical probabilistic pictures that one can draw of it under precisely are. Anyway, you said this is not a trivial thing.
Yeah.
So in place of dynamical quantities, I would say in place of Boobism's dynamical quantities statement, ours in cubism would run something like how you gamble on the outcomes of one measurement and how you gamble on outcomes of another measurement are not a priori related before you get to quantum mechanics. But the feature of quantum mechanics, the feature of quantum mechanical reality that rears its head is that how you gamble in this context should be related to how you gamble in that context.
Right.
And the particular way in which all of the gambles fit together reveals something about the world. In some way, it's a hidden ontic statement, I think. And it's not a trivial thing.
Yeah.
So there's a little more of a rhyme than I had appreciated between Boobism and cubism than today.
That's great. Yeah, I'm glad about that. Yeah.
Okay. Howard?
So perhaps related to the point that Chris just made, which I think I agree with entirely, it seems to me perhaps that what you've described could apply abstractly to any so-called general probabilistic theory, in that in these theories there are a variety of ways of measuring things on the system, and each way of doing it has to be described in terms of a probability distribution for the outcomes or the different processes that might occur. And that sort of the key ingredient to a reconstruction is explaining this bit about, quote, in the way described by quantum mechanics, or what's special about that way, and how is it different from the ways in which these relations also exist in any GPT state space, let's say, but what is special about the quantum relationships, and that reconstruction, sort of one version of reconstruction at least, latches on to trying to understand these special features of the way in which they're related to quantum theory in a more abstract framework, which I think is also consistent with a Boobist or Cubist even. Well, I don't want to say Cubist because maybe Cubist is more focused on the particularities of quantum theory. But yeah, this is sort of a way of looking at probabilistic coherence, of being probabilistically coherent in a world in which there are alternative measurements or processes that can go on that are not necessarily compatible through some single global distribution over everything. Thanks.
Yeah, thanks for that comment. I think that's right. Okay. I think so. In a sense, one can. I mean, I think the informational approach / neo-Bohrian approach that we're defending here has many analogies with operational approaches to reconstructing quantum mechanics. In the sense that we begin with some framework, some operational framework, and then try to distill what's real out of it. In the sense that the cubists also want to say. And so, yeah, the only small concern I have with GPTs, and I'm not sure if it really is a concern, but I forget who I was chatting with yesterday. So in the context of GPT, so what we want to emphasize here is that quote unquote local interactions are primary in the sense of you want that's where the tie to the empiricist methodology comes in, is the focus on local interactions, and the fact that these should always be possible to describe these in an effectively classical way, in the sense that so if you take the marginal of an entangled state, you have a classical probability distribution over pure states. And so there's an analogy there that you kind of recover these classical aspects, quote unquote locally. Right? In the context of GPTs, there are global things that are built into that framework. I don't know what to specify. I I wouldn't be able to specify what that is specifically, but I mean, it might be the case that in certain frameworks that they're like continuous reversibility, I think is an example that somebody mentioned. So for instance, these are global features of the framework that may not be as amenable to this kind of construal as some other operational frameworks, but I'm not sure about that. It's just, I just said it would depend on the framework, but as a general statement, I think I completely agree with what you said.
Yeah, I think maybe I wouldn't consider continuous reversibility as part of the framework, but rather as an assumption you might.
Right, okay, yeah, and in particular reconstructions. Yeah, that's right. Okay.
So I think of a very weak version.
Right.
Mike, thanks for the talk. So I have two questions. One is about probabilities. You mentioned that you take probabilities to be propensities, and I was wondering, well, why is that? What's wrong with the frequentist conception of probabilities? Is that compatible with your account? And the second question is a question about logic, actually. So the step that you take from your empirical methodology to its consequences, right? The idea that Boolean frames cannot be embedded in a global non-Boolean structure has a lot in common with the quantum logical interpretation, right? So quantum logical interpretation, as you know, the distributivity law doesn't hold; it's invalid, right? So that entails that some of the connectives are not true functional. They're not classical, right? Mm-hmm. So the question is, you committed to using a non-classical logic in quantum mechanics, or not?
So I'll start with the first question, just because I heard it last, but not necessarily, right? So everything I showed you in this talk has to do with classical probability and classical logic, and so So this you can think of this as a kind of quantum logical approach, but it's not a quantum logical interpretation in the sense in which that people wanted to defend in the 80s and so on. So I've cashed everything out in terms of the marginals, and that we can cash out marginal probabilities in terms of classically in this sense. So I would say not necessarily. It depends on the particular research program you're pursuing. Not necessarily, because I think we can say everything we want to say using classical logic and focusing on local operations. With respect to maybe you can follow up on that later if you want. But with respect to the question about propensities, I put it in quotation marks because I don't necessarily, like I said, I'm not necessarily tied to a Popperian interpretation of probability. Maybe on reflection I would be, I don't know, but I put it in quotation marks because what I want to convey here is essentially that these probabilities are thought of for us as objective, right? So like these conditional probabilities, in some sense, they're features of the world that we discover by setting up our experiment in a particular way, and we infer from the statistics that we observe to a particular probability distribution. So Michel Janssen, my co-author, is actually more sympathetic to frequentism than I am. I'm a little bit more sympathetic to what one might call a logical interpretation of probability, or like a twisted logical interpretation of probability. Whereas he's more sympathetic to frequentism. I don't think anything really hinges on that. I think the main thing for us is that probabilities are understood objectively, and that's maybe that's probably the main distinction between us and the cubists, for instance, where the cubists want to take a radical subjectivist interpretation of probability. So, but we aren't necessarily committed to propensities. But I think it's just helpful. It's a helpful way of thinking about what we mean by thinking of it in those terms. But we aren't necessarily committed to that interpretation of probability. But maybe on reflection we would be. I have to think about that. Does that answer?
I'm satisfied by the second answer to the first question, but about the first answer to the second question, I mean, I don't know. If you want to really be able to describe the non-Boolean global structure of events, right, you would have to use non-Boolean operators in your logic. So I don't see how you can avoid using non-classical logic, at least for that purpose. right?
I mean, that might be so. I mean, it's certainly in the context of...
And I mean that this is problematic.
yeah.
Because I mean, it's a radical change.
So it's problematic because it's radical, but I mean, we're not thinking of logic as something that exists in the, like, there's one true logic that exists in the world. Logic is something that we use to describe phenomena or describe our experience, right? And so, in that sense, I'm a pluralist about logical system, right? So I can use classical logic to describe my experience in the world, even in the context of quantum mechanics, in the way that I showed you. If you want some global logic to describe quantum mechanics phenomena, yes, that would have to be non-classical in some sense, right? So I'm not committed necessarily to any particular sense. It's a question that I may explore, or like somebody working in this program may explore in the future, but it's not something that we're necessarily committed to. So we're not concerned so much with that question, is another way of putting it. Yeah. But yeah, it's a very, very fair question.
Okay, Rüdiger.
Thank you. I have a question on probabilities that pulls in the opposite direction. Mm-hmm. When you say that a context fixes objective probabilities, so they can be derived from the context, and I would counter that even in any situation there would always be prior probabilities, even prior state assignments lurking in the background. That's certainly true in practice. I would argue that this is actually also true in principle. So that that you can actually never derive a quantum state from a classical context, but there's always, effectively prior state assignments, which is an argument that these probabilities will always be effectively subjective because dependent on the prior. So how would you respond to that?
Well, I mean, so that may be true. So I would need to think about that a little bit more. But I think that so the main idea that I'm trying to push here is that so the experimental context is really always effectively described. It's not. So the experimental context, when you describe your macroscopic measurement apparatus, that's always an approximate description, right? But to the relevant scale, we can think of it as a relatively solid understanding of our experimental context to the relevant scale that we're measuring. And so at that scale, one can think of these probability assignments as objective in that context. And that's all we mean, right? So I'm not sure if that addresses the question, but it comes back to the point that I made at the beginning that our interpretation begins from phenomena. We're not trying to build the world from the ground up. We're not trying to derive observations from the quantum formalism, right? We're beginning from something solid, relatively solid. Our classical state assignments, right? And so yes, there's all kinds of subtleties. Some subtleties that, for like I mentioned Curiel, and some subtleties that Eric gets into in his paper in the context of classical theory. There are always subtleties, of course, but we can think of them as relatively fixed because we're in the sense that we're relatively certain about how these apparatuses behave in certain contexts, like counterfactually, if we were to pull this lever or pull that lever. You know, what that would entail for the observation. So we can think of them as fixed in that sense. So with respect to that scale, with respect to that level of description, we can think of the probabilities of consequent apparent interactions with the quantum system as objective. But again, our philosophical conception is kind of the inverse of the normal philosophical conception, where you think of something as objectively existing, you know, like at a fundamental level in the world, and deriving observation from that. We begin from observation as fundamental, as objective in the sense that it's relatively fixed. And then we use quantum mechanics to relate those effectively classical descriptions to one another. I'm not sure if that answered the question or if it was orthogonal, but...
Certainly helpful, thank you.
Okay.
It was fun.
I can see that a Boolean frame is considered to constitute an observer. Is that taken as a primitive notion? And also by extension, could one say that a measurement apparatus is also defined the same way, and that's also considered in a primitive notion, which can't be reduced to anything simpler?
Well, the concept of Boolean frame is used as a primitive notion in this, on this understanding of quantum theory. But remember that this is an epistemic notion, right? So it's a frame that we impose on the theory. And so we take this to be minimal in the sense that all this gives you is like, it really relies on classical logic, right? In the sense that we have this Boolean frame that, given some commuting set of observables, we have yes or no answers to all the questions, which you can use and you can map those to computational states if you like, right? And so in that sense, it's fixed. Could there be a more refined notion of what observation means? Perhaps. We're not. I'm certainly not close to that possibility. But this is the frame that we're using, and we think it. So I mean, Bohr at certain times were like, we need to be able to describe what we have done and what we have learned, and arguably that presupposes a kind of Boolean understanding of the phenomena. Right? The phenomena are either within this range, the quantities are either within this range or they're not. Right? This Boolean yes or no classical logic sense that we use in the context of, everyday physics. And so, but it's an epistemic notion. The Boolean frame is an epistemic notion, and it plays a logical role in this interpretation. It's not something constitutive or a priori in some ontological sense.
And also we could think of that as a kind of epistemic requirement for the description of any physical phenomena. Right?
Yes.
Okay.
Yeah. I'd be interested to know how complementarity plays into your thinking. I view complementarity as really a principle which really allows us to tie together the different experimental perspectives. Mm-hmm. And in other words, complementarity is a very strong constraint or principle which says that all of these different experimental contexts are not sort of unrelated. They're all related in a very tight way. In some sense, all these different experimental perspectives ultimately reveal two distinct aspects, so to speak, of the underlying reality. So I'd be curious to know how that plays into your thinking.
Yeah, I mean, I think essentially. Hold on here. Oh yeah, I mean, I guess so. It's partly addressed here, right? So like these various ways that we can effectively describe phenomena in the context of an interaction. You can think of these as complementary descriptions of the system of interest. So that is an expression of complementarity, I would say, and especially here, I think, right? So in any given measurement context, we can in that context describe a dynamical model, an effectively classical dynamical model, and then you can think of the stochasticity of the observational results in that context as stemming from our inability to precisely specify some parameter in that model, right? So you can think of this in terms of the example that early commentators of quantum mechanics and Bohr as well use, like the wave versus the particle understanding of quantum phenomena, and that's essentially what I'm trying to say there.
Okay, thank you.
Welcome.
Okay, Howard?
So I guess I sort of had two issues, but about complementarity, I'm wondering, I was wondering actually, Philipp, if you had some more precise idea of what you meant by complementarity, because I just wonder if if there's actually something there that's stronger than just non-classicality, in the sense of if you say they don't all fit into one classical distribution, then maybe that is complementarity. It's just saying that there are at least two distinct Boolean frames, or is there something stronger about the relation that is?
I would say stronger. I would agree with Philipp, because it's not just that they don't fit together. It's that they do fit together in some way, right? So like there's.
But what about that way makes it complementarity as opposed to something else?
Well, what makes it complementarity, I would say, is the fact that one can consistently describe our observations in each of those ways in those contexts. So it's not contradictory to describe it in experimental context A in accordance with some given dynamical model, and in the context of in some other context in accordance with some other dynamical model, because of the uncertainty relations, in the way that Bohr argued in 28. I would say that.
Okay, I guess I'll need to understand more precisely what
Sure.
means.
Yeah.
Okay, so maybe you could say something very briefly on the relationship of your approach and Buddhism. So in contrast or in relationship to the standard objectivist interpretations, that's representational representations, because you said in terms of degrees of agreement, there's Bruckner-Zeilinger, there's cubism, there's relation quantum mechanics. What about many worlds, Bohmian? Would you say your approach is inconsistent with them, or would you say this is just a different methodology? As you explained, like the standard people would say, okay, here's objective reality, from this we want to understand how we experience the world. We go the opposite direction, right, like the cubists, here our experiences, now we want to understand the world. But yeah, my question would be, would you say that your approach is inconsistent with stuff like many worlds, Bohmian, or would you just say it's different methodology, there's an, yeah.
It depends on what you mean by inconsistent, right? So I mean, obviously, hidden variables approaches are consistent with the formalism, and in that sense, they're consistent with what we want to say, and also in a deeper sense, there is a consistency in the sense that, I mean, one can think of hidden variables approaches analogously to the way one thinks of, on our view, the way one thinks of reconstructions. Right? So we're reconstructing quantum mechanics in some external framework, and that can be very illuminating. So, for instance, when you're reconstructing quantum mechanics, or trying to, in using the local hidden variables model, yeah. So you get interesting results, such that as you increase the number of outcomes per ticket, you get closer and closer to the elliptoid. So these hidden variables models can be thought of as helping us to quantify the differences between classical and quantum mechanics, right? So they're very useful in that sense, and in that sense I endorse these kinds of approaches, these kinds of exploratory approaches of all kinds, including hidden variables. Where I get off the boat is the argument that insists that we need to be able to give some global picture of ontology in order to make sense of quantum mechanics. I think that's wrong. And I think that really, in principle, I could be convinced to be an Everettian. In principle, I could be convinced to advocate for hidden variables approach. Ultimately, what you would need to do to convince me to advocate for one of those approaches is to show me that it's useful for physics to pursue that. And I don't think that anything is gained in that way, aside from this kind of thing, aside from this way that it helps us to quantify how quantum mechanics departs from classical mechanics. So, for instance, if you want to convince me of Everettian, show me why it's useful to do that. Show me why it's really useful to do that in the context of quantum computation, right? Does it help us to understand how quantum computers work? Some people have made that claim. I think those arguments don't go through. But ultimately, I have that pragmatic perspective. I think that quantum mechanics is one of our most successful physical theories, and it's successful for a reason. And I think it's successful because it pursues this empiricist methodology that originates ultimately with Newton. And that's been and it's the methodology, not the metaphysical picture that some people say is behind it. That's responsible for the success of physics and science more generally.
Okay, perfect. So let's thank again Mike for the great talk.